Hello everyone, welcome back to my channel. Today we're going to go over finite element analysis of these sorts of problems where we have a few segmented rod connected to some kind of wall. So the goal of finite element analysis is to develop and use the finite element equilibrium equations for determining stress in an axially loaded structural member. So basically, we can treat each of these rods as analogous to springs, and because they're going to resist some force, so it's like each of them are some strings connected in series. And then since springs have a coefficient called K, which is the spring constant, if you remember from physics, we're going to have something similar in finite element analysis called the stiffness matrix K, which we will talk about later. And so let's say we have a rod that is axially loaded like this one. It's in tension, axially loaded. So this is almost as if we had a spring and we are basically pulling on it on both sides with the same force, which we will call P. And so in general, this rod can be treated like a spring having a stiffness given by the equation K is equal to EA average over L. So a key equation for finite element analysis is the equation the force matrix is equal to the stiffness matrix K multiplied by the displacement matrix U. So the finite element analysis, like its name, requires us to divide a given problem into a certain number of elements and a certain number of corresponding nodes. And the number of nodes will always be 1 plus the number of elements. Now, why is that? And what is an element? So when we talk about elements, we are talking about how many divisions we choose to give to our rod. So over here, it will be, for instance, since we since we want to use three finite elements, one element per segment, they already give us how to divide it into elements. So over here in this particular problem, AB will be the first segment, BC will be the second element, and CD will be the third element. Now, it is possible that you have a problem where they ask you to use, for instance, four finite elements where it's not necessarily that uh, one segment AB, one distinct segment as observed in the graph is going to be one element. For instance, we can divide our rod like this, where we have one, two, three, and four elements. So one, two, three, and four elements. But here they want us to use three elements, and they explicitly said to use one element per segment. So that's what we're going to do. And what is the number of nodes? The number of nodes is like at each point. So one node, this is the first node, this is the second node, this is the third node, and this is the fourth node. So as you see, the number of nodes is always 1 plus the number of elements. Since here we have 4 nodes, but 3 elements. If we were to use 4 finite elements, we would have 5 nodes. 1, 2, 3, 4, and 5. So keep that in mind. So here they already give us the number of elements, so we will be naming our nodes in order to keep track of where they are. So for instance, this one will be called x sub 0, and this one will be called x sub 1, this one x sub 2, and this one x sub 3. Wait, actually, hold on. I think I did that wrong. Actually, this one will be called x sub 1, and this one x sub 2, this one x sub 3, and this one x sub 4. And x1 will be equal to 0. Now, we have to define our stiffness matrix K. So each of these rods is going to have some spring constant because as we mentioned earlier, they behave like a spring, like a mini spring. So we will call K1 the spring constant of element 1, K2 the spring constant of element 2, and K3 the spring constant of element uh 3. K3 the spring constant of element 3, K2 the spring constant of element 2. And the generic formula for K is basically going to be EA average over L, as we see over here. So for instance, K1 is going to be equal to 2E times 2A divided by 4L, which is equal to EA over L. And then K2 is going to be equal to E times 3A over 4L is equal to 3 over 4 EA over L. And K3 is going to be equal to 3E times A over 2L, which is equal to 3 over 2 EA over L. Now it is time to define our stiffness matrix K, which is going to be kind of the big mama of these little Ks, is how I like to think of it. So the stiffness matrix K is given by, in general, it's given by first coming up with like this is our diagonal of the matrix. So the diagonal of the matrix is going to follow some specific pattern. So we're going to start with K1, and then this next entry down here is going to be K1 plus K2. And then this next entry is going to be K2 plus K3. And then this next one is K3 plus K4. Of course, we don't have a K4 over here, so we're just going to end with K3 without adding the K4 because K4 is basically equal to 0. It doesn't exist. And we continue going on this way like so with uh, basically the generic formula is given by Kn minus 1 plus Kn. And then we end with Kn over here. And then on the both sides of this diagonal going down, we're going to have also some sort of pattern going on. So for instance, to the right of K1, we are going to have negative K1. And on the other side, we're also going to have negative K1. And on above the K, next to the K1 plus K2, we will have negative K2. And over here we have negative K2. Over here we have negative K3. And over here we have negative K3. Over here we have also generically we're going to have negative Kn minus 1 and negative Kn minus 1. And then it's going to end with negative Kn and negative Kn. Wait, sorry. This one is supposed to be directly above negative Kn. And what about the other entries? We also have some sort of pattern going in the remaining entries down here. And these other entries, they're all 0. So we can simply write 0, 0, 0, basically 0 for everything until we reach the dimension of our matrix, which over here is infinitely expanding. Basically, all these other entries are just 0. Um, and to kind of indicate that we fill these with zeros, we are going to use dots to replace them. Okay, so that's our generic matrix. Now let's find the matrix corresponding to our particular problem here. Now, if we think about this intuitively, since we only have k up to k sub 3, this matrix will likely just end by kn is equal to k sub 3. So our matrix pertaining to this problem is going to be, oh wait, and yeah, our matrix pertaining to this problem is going to be equal to, remember we follow our generic matrix construction rules, which is good to follow to get used to it. Ooh. K1 plus K2, um, K2 plus K3, and then we end with K3. And then this entry is going to be negative K1. And then this other entry over here is negative K1. This here is negative K2, negative K2, and negative K3, negative K3. And then these other entries over here are zeros. So this matrix might look complicated to solve, but we can actually simplify it using our boundary conditions. And what do we mean by boundary conditions? We mean these conditions at A and D, because A and D are kind of like the boundary of our problem. And we note that these ends are actually fixed. So the displacement at A and D are going to be equal to 0. So basically UA equals UD equals 0. And if we go back to our equation over here, basically this is saying that the force is related to the stiffness matrix times U. And here our U vector is actually equal to U1, U2, U3, and U4, since there are 4 nodes. However, since the displacement at A and D, which corresponds to U1 and U4, are actually 0, the first row and first column and fourth row and fourth column of our stiffness matrix is going to become useless and in solving for the first part of our problem, which is which is solving for the displacements at B and C. Basically, the first row and first column and fourth row and fourth column of our stiffness matrix are useless for solving for these displacements, but they are useful, or they are going to be useful for solving for the reactions at A and D. But for question part two, we can cancel out thus the first row and first column and fourth row and fourth column of our matrix. Note that this doesn't mean that the first row and first column and fourth row and fourth column of our matrix are zero. This just means that they produce useless equations for solving the displacements at B and C. So our stiffness matrix gets simplified to K plus K2. Looking at this area over here, it gets simplified to this matrix basically. K1 plus K2, negative K2, negative K2, K2 plus K3, and sorry, this is K1. And we can now plug in our coefficients for K1 and K2. So note that K1 and K2 are expressed in terms of EA over L, but K1 can be expressed as EA over L times 1, and K2 can be expressed as EA over L times 3 over 4, and K3 as EA over L times 3 over 2. So those are the coefficients of those matrices, and we can factor out EA over L here. And write EA over L times the coefficient of K1, which is 1, the coefficient of K2, which we found to be 3, 4, and the coefficient of K3, which is 3 over 2. So K1 plus K2 is thus equal to 1 plus, what was it again? 3 over 4. And then we have negative 3 over 2, um, negative 3 over 2, and then we have 3 over 2. Oh, wait. Oh, sorry. Actually, the K2 is negative 3 over 4, as we just said. And K3 is 3 over 2. Yes. So then simplifying this matrix further, we will get it's equal to 7 over 4, negative 3 over 4, negative 3 over 4, and 9 over 4, all multiplied by EA over L. Um, all right, so we've enforced the boundary conditions, and now we want to solve for the displacements at B and C. But first, in order to do that, we have to find our force matrix. So let's go ahead and find the force matrix first. All right, so in order to do that, we have to draw a free body diagram, or it would be helpful to draw a free body diagram of our axial system over here. So let's go ahead and do that. So basically, there are 3 rods in our system connected in series, and at the 2 ends, there are going to be reaction forces. And we're going to define our positive axis as x is positive to the right and y is positive upwards. So intuitively, PD will be pointing to the right, and PA will be pointing to the left. And these are our reaction forces at each of those points. We have a force PB applied at node 2, PB. Oh wait, actually no, sorry. We don't have a force PB applied at node 2. But for the sake of our free body diagram, we want to draw the PB force there, we want to draw the force applied at each node because our force matrix is going to be basically all the external forces on the system. All the external forces applied on the system. And our system is considered to be this rod over here. So basically PA and PD are external reaction forces, and 2P is the external applied force. Now, is there an external force applied at node 2 that will constitute our PB? Well, no. So that entry is just going to be 0. So our force matrix, which we commonly represent with curly braces, is going to be equal to our force at each node. And because there are 4 nodes, there are going to be 4 entries. First is going to be the external reaction force at PA, which because we took our positive convention to be positive to the right and PA is pointing to the left, is going to be negative PA. And then we have 0 at node PB because there's no external force applied at node 2. And we're going to have negative 2P at node 3. And finally, at node 4, we are going to have positive PD. Now, similarly as before, we're going to go ahead and apply our boundary conditions to our force matrix as well, which because the end at node 1 and 4 are fixed, we can cancel out row 1 and row 4. Now, remember that this does not mean that the reaction force PA and PD is 0. It simply means that because the displacement at node 1 and node 4 are 0 because those ends are fixed, they're not going to give us useful equations for solving for the displacement at node 2 and node 3, which corresponds to our point B and BC, to our point B and C. So when we go ahead and write out our matrix applying the force matrix equals the stiffness matrix multiplied by the displacement matrix, we are going to have, and remember that applying our boundary conditions to our displacement matrix, we can cancel also the first row and fourth row because they don't give us useful equations either in the context of solving for the displacements at B and C. So we're going to have the force matrix reduced to 0 and negative 2p. And this is going to be equal to the stiffness matrix, which we found to be 7 over 4, negative 3 over 4, negative 3 over 4, and 9 over 4 multiplied by the displacement matrix, which is going to be U2 and U3, which is corresponding to UB and UC. The displacement at UB is characterized by UB, and the displacement at C is characterized by UC. And don't forget to multiply by the EA over L constant as well, because this matrix is multiplied by EA over L. Every single entry is. So we're going to go ahead and add that over here. Oops, or I think it'll be more correct to add it over here. So I'm also going to clarify something. So the entry for the second node is 0 because there are no external forces applied at point B. Although this does not mean that there is no internal force. There is of course going to be an internal force at point B, but since this matrix F is only a matrix of external forces applied on our system, which we treat it to be this 3-element rod, we do not include the internal forces in this entry. So now we can solve this matrix by performing some matrix multiplication. So we're gonna get EA multiplied by each of these entries, remember? And this And then we're going to get each of these entries after you multiply by EA over L multiplied by UB plus this entry multiplied by UC, and the same thing on the bottom row as well. So we are going to get 7 over 4 EA over L UB minus 3 over 4 EA over L UC. And this entry is equal to 0. And on the bottom row, we have that negative 3 over 4 EA over L multiplied by UB plus 9 over 4 EA over L UC is equal to negative 2P. So that is just our classic system of equations now. And from over here, we can have UC is equal to 3EA over 4L multiplied by 4L over 7EA. And all this multiplied by, uh, oh wait, sorry. This one is supposed to be UB. So UB equals that multiplied by UC. And thus UB is equal to 3 over 7 UC. And from the second equation, we can plug in 3 over 7 UC for UB to get negative 9 EA over 28L UC plus 9 over 4 EA over L times UC is equal to negative 2P. And thus solving for UC, we get 54 over 24 over 28, sorry. EA over L UC is equal to negative 2P. And thus UC is equal to negative 28 PL over 27 EA. And then using our relationship between UB and UC, we can also find that UB is equal to 3 over 7 times this value, which is going to be negative 4 over 9 PL over EA. And thus we have solved for our two displacement values now and completed part 1 of our question. So for the last part of our problem, part 3, finding the reactions at A and D, we're going to use the two equations we crossed out from earlier. Remember that from previously we crossed out row 1 and row 2 because those equations were useless for solving the displacements at B and C, but they are going to be useful for solving for the reactions at A and D. So for part 3, we want to Remember our matrix F is equal to negative PA 0, negative 2P PD, and our matrix K. So our matrix K was this matrix over here. So now we are not going to cross out the first and fourth rows anymore. So basically, K multiplied by the displacement vector UA, UB, UC, UD, where UA, UB, UC, UD are the displacements at each of these points, is going to be equal to negative PA 0 and negative 2P D. But notice that UA and UD, as we found earlier, are 0 since those ends are fixed. And thus, if we think about how matrix multiplication works, basically we have this matrix, the matrix K multiplied by the displacement UA, UB, UC, and UD. So if UA is 0 and UD is 0, we're going to have K1 times 0, negative K1 times 0, negative 0 times 0, and 0 times 0 on the first row, and 0 times 0, 0 times 0, negative K3 times 0, and K3 times 0 on the bottom row. So the only rows that are going to be left is these two rows over here, and those are the rows that we are going to be using. Sorry, so the K matrix is obviously not equal to this, so I replaced it with an arrow showing you the next step in the process. And as mentioned previously, all the first row in the entries are going to be 0. Wait, actually, I made a mistake there. So matrix multiplication does not work like that. We have the K matrix multiplied by 0, UB, UC, and 0. So we're going to have 0 times K1 minus K1 times UB times 0 times UC times 0 times 0 is equal to negative PA. And our other two rows are the ones that are useless in this case, since we don't have a reaction force in this entry and that entry. So it's not going to give us an equation from where we can solve for our reaction forces, PA and PD. So we're only going to be using the for row 1 and row 4 in this part of the problem. Sorry for the confusion. Yeah, so basically multiplying our matrix K, and we can choose to consider only these two rows now to save time writing the whole matrix. And just cross out the second and third rows. multiplied by 0 UB. Oh wait, yeah. We cross out the second row and third row also over here. And this is equal to negative PA. And note that the curly braces and the brackets really, they're just ways to represent the same matrix. So it doesn't really matter which one you use, I guess. And then performing matrix multiplication, we have oh wait, hold on. Actually, these two entries do matter. UB and UC. Because they give us a one equation that will equate to negative PA. So we have 0 times K1 is 0 minus K1 times UB plus 0 times UC plus 0 times 0 is equal to negative PA. And we get that from the bottom row, 0 times 0 is 0, 0 times UB is 0. UC times negative K3 is negative K3 UC plus K3 times 0 is 0. And this is equal to PD. So we see from here that PA is equal to K1 UB and PD is equal to negative K3 UC. And plugging in our known values for K1 and UB, we get that it's equal to EA over L multiplied by negative 4 over a PL over EA. And certain things cancel. The EA's cancel, the L's cancel. And we are left with negative 4 over 9P. And for our PD, we get that it's equal to negative 3 over 2 EA over L times negative 28 over 27 PL over EA from before. And this is equal to 14P over 9. So thus we have solved the second part of this problem, the last part of this problem, I mean. We have solved for the reactions at A and D. So thank you guys so much for watching this video, and I hope it was helpful to you. As usual, if you have any questions, feel free to ask me in the comment section. And I've also linked the link to this presentation and this whole writing in the comment section of this video. Thank you guys for watching again. See you in the next video.